Right, well by now we should be sufficiently well practiced at creating partial fractions from fractions with various different factor denominators. What we're going to look at in this final example is an application of where we can take these partial fractions. And one of the most common uses is to come up with binomial approximations to complex algebraic fractions. So we're going to look at this example, we're going to break it into partial fractions, and then we're going to look at how we can use binomial expansion to come up with a quadratic simplification of it. So if I just write down what the function is. So part A, express the function in partial fractions. Okay, well, the linear factors, so that's a straightforward equivalence. Combine them. I'm going to compare coefficients. No quadratics. So power of 1, I'm going to have minus a minus 2b from that one equals 1. And the constant, I'm going to have 2a plus 3b equals 0. From 1, a will be minus 2b minus 1 into 2 lots of a plus 3b equals 0, minus 4b minus 2 plus 3b equals 0. So from there I'm going to have minus b equals 2, so b equals minus 2. Put that in 3. And a will be minus 2 times minus 2 minus 1, which will be 4 minus 1, which is 3. So therefore fx can be written as a 3 over 3 minus 2x plus b over 2 minus x. So that's part A done. Part B, expand fx in ascending powers of x to produce a quadratic approximation. Okay, well, there's a huge leap of recognition there, apart from we're smack bang in the middle of work on partial fractions and binomial expansion. But if that was in the middle of an exam paper, you would have to recognize the next step. So the next step is to write these fractions in index form. So I can write that one like that by bringing the denominator up and having it to the power of -1, and the same with this one. Now we're looking for a binomial expansion, and we need to recognize that because we haven't got positive integers, we have to use the general form of it, which we can't do unless it's 1 plus or minus some form of x. So with this one, I have to take out the 3. So there's that 3 there, I'm working in here. When I take out the 3, I have to write it like that. Check when you multiply that in. 3 minus 2x, and that's going to be all to the power of -1. And we have to do the same with the second one. So we take the 2 out, check, 2 times 1 is 2, 2 times that is minus x. Then that to the power of -1 we can apply separately to each factor in turn. So we get 3 to the -1, minus 2 to the -1. I'm writing every possible step here. Depending on your level of confidence, there are shortcuts that you can take. 3 to the power of -1 means reciprocal. So 2 to the -1 is the same as a half. They will cancel, leaving me 1 minus 2/3 x to the power of -1, which I can now expand. And similarly here, which I can also expand. So I'll take each of those separately as a binomial expansion. And we want to produce a quadratic approximation, so we need to expand in powers up to x squared. So first of all, if we expand 1 minus 2/3 x to the -1, n is -1, x is all of that. The expansion is 1 plus nx plus n minus 1 over 2 factorial x squared. And that's as far as we need to expand it, because we're interested in up to quadratic. So we just show that that continues infinitely by putting the dots there. Let's make it a little bit prettier. 1 minus and minus is a plus 2x over 3. That's going to be positive, that's going to be positive. 2 factorial is 2, they cancel out. 2/3 squared is 4/9 x squared. We have to remember that that's only valid for particular values of x, so we need to include the validity, and it's valid for modulus of all of that must be less than 1, which is the same as that, because minus 2/3 is a constant which we force to become positive, giving us that x must be between -1.5 and 1.5. So if you want to write it like that, or if you want to write it like that, it doesn't matter. So that is what we can replace this part by. We now do the same thing for the other part. So expanding 1 minus x over 2 to the power of -1. 1 plus n x plus n minus 1 over 2 factorial x squared plus 1 plus x over 2, that's going to be plus, that's going to be plus, they'll cancel, x squared over 4. And this one is valid for which is the same as so it's valid for modulus of x less than 2, or if you're happier writing it as a full inequality. So when we combine these two expansions, the finished expansion, the combined expansion, will be valid for the strictest of these two conditions, and that would be this one. Values of x between 1.5 and minus 1.5 satisfy both sets of conditions, whereas if you were looking at this one, if you had a value of x of say 1.6, well, it would satisfy that, but it wouldn't satisfy that. We'll talk about that when we come to the finished expansion. So what we now need to do is going to approximate, because now I'm combining these two approximations. So the first one is this 1 plus 2/3 x plus 4/9 x squared, and I'll just group it in a bracket, minus the expansion of that. So minus this expansion, 1 plus x over 2 plus x squared over 4. So when we simplify that, I have 1 minus 1, so the constant term goes. I've got 2/3 less a half, so 2/3 less half, which is a sixth. So x over 6, and then 4/9 x squared minus a quarter. So 4/9 minus a quarter, (7 over 36). X squared. And that is going to be valid, as we discussed, by the strictest of the two modulus of x is less than 3 over 2. Okay, so let's go back to the question. We've done partial fractions, we've done a quadratic approximation, state the range of values for which it is valid, done that. Calculate the relative error in this approximation when x equals 0.1. Okay, so when x is 0.1, into the original function will be 0.1 over 3 minus 2 lots of 0.1 times 2 minus 0.1. We'll do this in the calculator. Now hopefully you know how to allocate variables, but in case you don't, I'm going to allocate the value of 0.1 to the variable x in the calculator. And the way that I do that is type in 0.1, and then store is above this recall button. So shift store, and then I'm looking for the pink letter x, which is above the open closed bracket. So you just press it, and that now stores 0.1 in the x variable. That allows me to write my function exactly as I see it on the page. So open bracket, alpha this time to get the x on top, and then on the denominator, open bracket, 3 minus 2 alpha x, close bracket, open bracket, 2 minus alpha x, close bracket. So that's exactly the function I've been given, and I've defined x as 0.1. Press equals, works it out for you. And I'm going to store that in another variable, so I'm going to store that in a. So shift, recall for store, and then just press the letter A. You don't have to alpha it, so answer is stored in A. Then I'm going to go to my approximation. So in my approximation, it's going to be x over 6, 0.1 over 6, plus 7 over 36, 0.1 squared. X is still defined as 0.1, so I'm going to worry about typing that in. I can just write it exactly as I see it. Alpha x over 6 plus fraction 7 alpha x squared over 36. So my approximation is that. I stored that in A, and I'm going to store this in B. So shift, recall to store it, and in B, so that's stored in B. So now to work out my relative error, I have to work out the difference of the two values. So B minus A or A minus B, it doesn't matter, divided by the actual value, which is A, times 100. And because I've stored as an A and B in my calculator, I can just use them. So open fraction, alpha B minus alpha A over alpha A times 100. So the error is 0.99%. So it's less than 1%. The negative just means that one is bigger than the other. So if I had done A minus B, it would have given me a positive. It doesn't matter, it's the absolute value that we're interested in. So that now we're up to a pretty detailed A-level type question, where it's testing your ability to work with partial fractions and binomial expansion.